Giuseppe?
Okay, once again, I should share the screen. Let me repeat the whole procedure before. Open with preview. Okay. View, enter full screen. Is that okay?
That's okay.
Can you hear me? So we can start?
Yes, please, you can start.
Oh, okay. So in the second part, I'm not going to focus on explicit potential estimates as before, but on how to use potentials and nonlinear potentials to provide new regularity estimates, this time for the emphasis being on non-uniformly elliptic problems. Okay, so this time, don't ask me why, but I will concentrate on minimizers of integral functionals. Well, you can actually ask me why, because for under the growth conditions and the non-uniformly elliptic conditions, and I'm going to consider, it's better, the notion of minimality is more natural, because otherwise the notion of energy solutions must be very much detailed, and there is no room for doing this in an expository talk. But anyway, at the level of a priori estimates, we can also go directly to equations. And of course, the catch is given by the so-called Euler-Lagrange equation. So when you look at this functional, you can also think of equations like this, where this is the Euler-Lagrange equation of the functional. In particular, if this is the dw to the p, then this is the p Laplacian operator. Okay, let me go back to the definition of uniform ellipticity. So if you take a linear elliptic equation, when mu this time is a measure, it's not a measure, but it's a matrix, it's a symmetric matrix. So this is called uniformly elliptic is the ratio, the dispersion rate of the matrix is bounded. So the ratio between the highest and the lowest eigenvalue is less than or equal than a certain constant. And it's otherwise called non-uniformly elliptic if this is not true. Now, if you want to extend this notion to a nonlinear equation, you have to go to the linearized equation. That is, if you want to know, if you want to have estimates for the gradient, as usual, you have to differentiate the equation. And therefore, the differentiated equation, when you differentiate, for instance, with respect to some component, to some direction S, can be written in the following way. And therefore, you go and look at the eigenvalues of this matrix, the matrix of first derivative of this vector field. This is a vector field that goes from Rn to Rn, and therefore this is a matrix n times n. And therefore, what I'm going to do is the following. I'm going to consider conditions like this, where G1 is a function depending on x and z that plays the role of let's say, the lowest eigenvalue, and G2 plays the role of the highest eigenvalue. And this, of course, happens for the functionals, for the case of functionals, to when you look at the Hessian of the integrand. Okay, G1 is the lowest eigenvalue, G2 is the highest eigenvalue. And the ratio, the ellipticity ratio, is given by the ratio between these two quantities. And when this ratio, when z is the gradient variable, when this ratio is uniformly bounded, then you are in presence of uniform ellipticity, as before. Otherwise, we call it non-uniform. So non-uniform ellipticity is a more general condition of uniform ellipticity. It allows many more structures, as you can easily imagine. And it's also a classical problem. It's a much more dynamic condition, in the sense that uniformly elliptic equations are much more rigid, and non-uniformly elliptic equations are much more, let's say, flexible. And okay, it's a very classical topic. It's a very classical topic. Why? Because, for instance, the minimal surface operator is a non-uniformly elliptic operator. It has been studied since the 30s, and but it's not the only one. So there's a very large classical literature on non-uniformly elliptic operators. For instance, like Giuseppe, Alceva, all these names are this is very, very classical. And more recent or more, okay, less old results are given by these authors. And so let's say it's a very classical topic. For instance, both the theses of Neil Trudinger and Leon Simon are on this topic, exactly on this topic. In particular, the famous Michael Simon inequality on manifolds was proved in order to treat certain general non-uniformly elliptic equations of the type of minimal surface operators. This is the original thesis of Leon Simon, extending a paper by Lagiszewska and Alceva. Okay, so what is the point here? Is that the ratio might blow up. Okay, the first thing usually the ratio blows up when the gradient is large, when the variable is large. And in particular, you can replace the notion of non-uniform ellipticity just by looking at when the gradient is large. So in particular, for non-autonomous functionals, non-uniform ellipticity means that this soup is plus infinity. And now you see that there is a competition here. Why? Because on one hand, you would like to prove, when proving regularity of solutions, that the gradient is bounded. So you have to prevent that the gradient becomes unbounded. But when the gradient becomes unbounded, the ellipticity ratio is also unbounded, gets also unbounded. But the ellipticity ratio is the quantity that appears in all regularity estimates. So there is a competition between the two. Because the gradient tends, you want to limitate the growth of the gradient. But if the gradient gets too large, then the ellipticity ratio gets large. But on the other hand, you need bounds on the ellipticity ratio. So this competition usually results in all kinds of assumptions in the literature in this kind of growth conditions. If you look at the literature, then all these authors and papers, they put several definitions, but eventually everything boils down to prescribe a growth several times a polynomial type on the ellipticity ratio that tells you that the ellipticity ratio cannot grow too much with respect to the gradient, because otherwise regularity breaks down. So in particular, they prescribe that the ratio blows up with the small power of the modulus of the gradient. So in particular, if you prescribe that the lowest eigenvalue grows as like p minus 2, and this like q minus 2, and p is strictly less than q, then the only bound you have is like this, and you cannot allow that q is too much larger than p. And the issue is how much larger can q be than p. So this is a main condition on non-uniform ellipticity. So it's a structural condition on the operator. And in particular, in the autonomous case, there's a large literature on this. In particular, these are structural conditions that tells you that if you consider minimizers of solutions to the Euler Lagrange equation of functions like this, that satisfies these two types of conditions. So these are called PQ growth conditions when considered on F, and non-uniform ellipticity conditions when considered on the Hessian. Then conditions like this, where this object goes like 1 over n, is necessary and sufficient in order to get regularity. And this was, you can find positive results and counterexamples by Giaquinta and Marcellini, and positive results original by Marcellini. But there's been a lot of developments. In particular, the sharp condition allowing for Lipschitz continuity is not known for the gradient under these general conditions. The best results that I know are due to Bell and Schaffner in these two recent papers. when they find an improvement of the original Marcelling is bound. And on Cristiana De Filippis, Lucas Koch, and Jan Christensen on a recent very delicate paper published in Archive for Original Mechanics and Analysis this year. That's a very, very delicate and deep paper by De Filippis, Koch, and Christensen. These are papers that I strongly recommend you to give a look if you're interested in this, because they give a full flavor of the results, starting by Marcelling and ending up with these papers by De Filippis, Koch, and Christensen. In particular, this paper contains very, delicate and refined techniques using certain delicate versions of so-called Gering's lemma and the duality principles, convex duality principles. Okay, now the problem I would like to address is the one of Schauder theory. Schauder theory has been originally an open problem in non-uniformly elliptic theory. Now I'm considering minimizers, or if you like, solutions to the Euler Lagrange equations. And there are two kinds of conditions here. These non-standard growth conditions, where you can bound this when z is larger than 1, because we are looking at the gradient boundness. Because when the gradient then is not bounded, then these equations become again uniformly elliptic in a sense. So the focal point is really getting L infinity bounds for the gradient. So there are no standard growth conditions and no uniform ellipticity like this. Oh, what happens here? Oh, something happened. Okay, so the question is, does Schauder theory hold, and under which assumption? And Schauder theory, it's something that relates the regularity of solutions with the regularity with respect to x. Okay, let me give a brief recap of what is classical Schauder theory. So Schauder theory is the following. The idea is the following. You take an autonomous equations like this, and then you add coefficients, and you want to know how the regularity of coefficients influences the regularity of solutions. So the idea is that you take this equation, you insert coefficients, and you want to know how the regularity of coefficients influences the regularity of the gradient. Okay, in this particular instance of Schauder theory, you see that since the matrix mu and the gradients, they stick together, then you would expect that the gradient is no more regular than mu. What mu is. In one dimension is very simple, because you solve, for instance, like having du like 1 over mu, and it's there. Okay, in fact, what you can prove here in the local versions, global versions, depending on regularity of the boundary, but I'm here interested in local versions, then you can go up to the boundary once again. Okay, what you can prove is this classical statement. If coefficients are C0 alpha, then the gradient is C0 alpha, provided alpha is less than 1 and larger than z. And then similar results are old for non-divergence form. In that case, you go to second derivatives. Okay, this is a classical topic developed since the 20s by Hopka, Ciopoli, Schauder, Giraud, but then there is a lot of people like Admon, Gaglis, and Ehrenberg extending to the vectorial case and so on. And whatever you do, and of course, there are Schauder estimates these days for every kind of operator. In the subelliptic case, in Monge-Ampere, whatever you do, there are Schauder theory. But all these theories are unavoidably based on the fact that on perturbation methods. Perturbation methods means that you freeze coefficients, you locally compare solutions to your solutions to equations with frozen coefficients. And then since coefficients are oscillating very little, then solutions differ very little. And then regularity of solutions of original equations is inherited by comparison from the regularity of solutions to constant coefficients equations. And the original proofs by Hopf, Schauder, and these people were via potential theory. But now we have faster ways to do it. For instance, Campanato did it in a very nice original way, introducing suitable function spaces, incorporating the notion of Hilbert continuity into integral decay estimates. Schrödinger gave an estimate via convolution techniques. Leon-Simon via blowout methods, which is another way to make comparisons, this time by contradiction. But all these proofs, they rely on perturbation and comparison methods. In particular, you have to match comparison estimates with decay estimates, and you can match and iterate these only if and only if these estimates are homogeneous. But homogeneity of a priori estimates only happens in the uniformly elliptic case. And that's why this theory was only a uniformly elliptic theory. And this can also be done for nonlinear equations. And this is essentially a fundamental work by Manfredi in the 80s, who did this in his legendary PhD thesis. But once again, the idea is that, for instance, you can get Schauder theory for P-Laplacian operators. That's what Manfredi did. And you can also extend this theory like Lieberman did. But once again, the idea is that you freeze and compare and everything must be uniformly elliptic. The P-Laplacian operator is another instance of uniformly elliptic equation. It's degenerate, but still uniformly elliptic because the ratio between the largest and the lowest eigenvalue is essentially a constant. It's not really a constant, but it's bounded by two different constants. Okay. Okay, so this is the thesis of Manfredi. And if you want to learn about the basics of P-Laplacian regularity in the scalar case, you can look at this. It's written very carefully, and it's a very worth reading thesis for those who are beginners who want to learn the theory. It's written in a very clear way. I actually don't know many places. I don't know other places where it's written better. Probably this is. Okay, now let's go to the non-uniformly elliptic case, because the problem is that, okay, we want to address now the problem of Schauder theory in the non-uniformly elliptic case. So let me consider this nowadays very popular double phase functional. This was firstly considered by Zhikov in the setting of elasticity, homogenization, Lorentzian phenomenon, and so forth. So this is essentially a combination of two different P-Laplacian type energies with different rates, P and Q. And it's very good to, for instance, to model strongly anisotropic materials when you make mixtures of materials with two different hardening exponents. So the peculiarity of this is that pointwise is that when A is 0, the integrand looks like the P-Laplacian, otherwise looks like a Q-Laplacian. So it's a combination of the two. And I'm always considering this when A is C0, is C alpha for some alpha. Not necessarily between 0 and 1 at the moment. Okay. So, for instance, this is an example when you consider a material of two different a mixture of two different materials, a Republican material and a democratic material. This is called Zhikov's checkerboard. It's very important in this in these things. In this topic, it emerges in homogenization, and you can look at this classical book by Zhikov, Kozlov, and Olenik. Okay, the double phase functional is still uniformly elliptic, because if you compute pointwise the ellipticity ratio, this is uniformly bounded. On the other hand, it only satisfies no standard growth condition. So it is something in between classical non-uniform ellipticity and non-uniform ellipticity, because according to the usual definition, is still uniformly elliptic, but it exhibits a certain non-standard growth condition. In particular, with Cristiana De Filippis, we gave a weak notion of non-uniform ellipticity, which is able to capture some non-uniformly elliptic properties of this functional deriving from its unbalanced growth conditions. Okay. So it's so the idea is that this is a uniformly elliptic functional. It generates a uniformly elliptic order Lagrange equation. You have Elder coefficients, so the gradient should be Elder continuous because it's uniformly elliptic. But then there is this very disturbing counterexample we found many years ago together with Fonseca and Malin. So you see, Mali, who unfortunately passed away not long ago, was a key figure in this nonlinear analysis because it appeared already in this potential estimate. It reappears here. It's one of the sharpest brains I've ever seen in my life. Okay, and then we constructed even a non-degenerate version of the previous functional with exponents satisfying this condition. And the point is that you can find minimizers, so solutions to the Euler-Lagrange equation, distribution of solutions to the Euler-Lagrange equation, which are discontinuous on a set of arbitrarily large capacity. Any minimizer makes the energy finite, so it's in W1P because this contains W1P. So the set, the Hausdorff dimension of the set of the essential discontinuity point cannot exceed n minus p. And then you can go as close to n minus p. But anyway, solutions are discontinuous. So you have an example of a regular equation with Euler continuous coefficients uniformly elliptic for which Schauder theory fails. In particular, the first, we constructed this example building on previous work by Zhikov in a two-dimensional work on a Lorentz phenomenon. Then with Esposito and Leonetti, we first constructed the one-point singularity and a solution which is not in W1Q. And then Balcidini and Surnachov extended our result up to the maximal dimension and getting no higher integrability whatsoever. Therefore, we have constructed an example of an elliptic equation, which is uniformly elliptic, which is analytic with respect to the gradient variable, whose coefficients are Hilder continuous and are as regular as you like, but minimizes and solutions can be as bad as any other W1P function. So this is and this can be done just by speculating on this very simple structure. Of course, you have to cook up a suitable coefficient, very bad coefficient, whose geometry has something reminding this Zhikov checkerboard, but on fractals, You have to construct these checkerboards on fractals with maximal dimensions. And this is very shocking because it contradicts all kinds of orthodoxy. By the way, if we look at all the counterexamples, we see that this condition is satisfied. So in all such counterexamples, this condition is satisfied. So Q over P is too large, and this largeness depends both on the dimension and now also on the rate of Hilder continuity. So on one hand, we have an open problem with the lack of Schauder theory, and we have an example that Schauder theory in general fails for uniformly elliptic problems. Now we go back and we want to find good answers to this problem. And from now on, I will consider it on genuinely non-uniformly elliptic problems. And I will consider just this model example. It's a model example. We can extend this to more general example, but for expository purposes, it's better to frame this example, to concentrate on this example that from the regularity viewpoint already contains all possible difficulties at the level of a priori estimates. So we consider a genuinely non-uniformly elliptic functional with P different than Q, and just we had a Hilder continuous coefficient. It's as simple as this. For minimizers of these functionals, Schauder theory is an open problem, even the gradient boundless. Okay, the first sign that this is, you can do something below this condition was obtained by Esposito, Leonetti, and myself. And we proved the following result. If you have a coefficient, which is C0 alpha, non-uniform ellipticity with two different exponents, and if you contradict the bound given by the counterexample, then you can bootstrap the integrability from W1P to W1Q. At least we have the bootstrap of integrability, but you are still ideas far from gradient Hilder continuity or gradient boundless. But this is the first sign that the phenomenology of the previous example could be excluded. And this is in the same paper where we constructed the first example. So we both constructed a counterexample showing that you get you fail to be W1Q, and then we constructed regularity. And this extends also to the double phase function. Okay, in particular, the classical fact is the following. Take a uniformly elliptic equation, and Manfredi's result tells you that you have Elder continuity of the gradient. Take a non-uniformly elliptic coefficient, a tensor field, where the ratio grows like this, and this is not known. This is an open problem. This is a particular instance. These are the general open problem that you have. This open problem appeared several times in the literature because, of course, shadow estimates are very foundational in elliptic theory. And if there are no known, people ask whether they are not unknown. It was essentially, if you look at all the papers in non-uniformly elliptic theory, they do not allow Hilder continuous coefficients. Coefficients must be smooth enough, but not Hilder continuous coefficients. For instance, this was observed in this paper, in this review by Lieberman on the paper of Giaquin Giusti, where they proved where they gave in the non-degenerate case the first proof of nonlinear shadow estimates, and of course Lieberman observes that when these conditions of uniform ellipticity fail, either you already assume that the gradient is bounded, but then you go back to uniform ellipticity, or otherwise these techniques, they cannot work. This also appeared in this classical book that makes a summary of the work in Lagiszewskaja's lab in St. Petersburg from the 70s by Ivanov. And Ivanov presents this theorem of Lagiszewskaja and Duhay-Alceva, where you see they have to assume that the gradient is bounded. So in a sense, they go back to uniform ellipticity, and then they have to assume that the coefficients are differentiable, but non-Hilder continuity. And in particular, once again, also Ivanov observes that either you assume that the gradient is bounded or there's nothing to do. And also, Giaquin and Giusti themselves observed that their techniques, they fail when you do consider, for instance, not uniformly elliptic problems. So this was a very long-standing open problem. And if you want, so finally, after many years of studies, we were able to give an answer thanks to the driving force of Cristiana De Filippis in these 3 recent papers that you can find in these journals. And then there are two brief summaries, one appearing on the notices of AMS and the other one of the European Mathematical Society magazine by De Filippis. And you can find solutions finally in these papers that also build on previous work on the linear potential theory that you have seen in the previous talk. Okay, the theorem is as simple as you can imagine. So you get this uniformly elliptic integrand, non-uniformly elliptic integrand. So we pick your growth conditions. A Hilder continuous coefficient, alpha is between alpha and 0 and 1. So alpha here is between 0 and 1. It's not 0, it's not 1, it's in between. And you assume the optimal bound, otherwise no way. And then you can prove that if coefficients are Hilder, then the gradient is Hilder. Not with the same exponent, because at this stage we are still allowing degeneration, and the P Laplacian does not allow you to do this. But you can prove that if coefficients are Hilder, then the gradient is Hilder. And you can prove it with the optimal bound. This is a major fact here. You can prove it with the optimal bound. You can find this in this recent paper on Duke Journal, which is essentially which went in print last month. And of course, when you go to non-degenerate equation, then you can recover the classical shadow theory. That is, the assumptions are the same. This time is non-degenerate, so it's never 0. And then you can recover the same exponent. So you cannot do better. So this is optimal in the input and optimal in the output. So how this is done? This is done by reversing a classical principle that was adopted in regularity since the 20s of the past century. So the problem is the following. Consider an equation with elder continuous coefficients. How do you get an L infinity bound, an L infinity a priori bound on the gradient? So in general, what you do, you prove first that the gradient is elder continuous, and then from these you get an a priori gradient bound. Because you cannot differentiate the equation because coefficients are not differentiable. So you go by perturbation. But if you go by perturbation, you use Schauder theory. So to get L infinity bounds on the gradient, you need Schauder theory. So you first go to C1 alpha, and then you go to L infinity bound. In this approach with Cristiana De Filippis, we reverse the strategy. And this is the first time since the past century I know that this is done in general. So the classical way is that C1 alpha estimate imply gradient estimate. We give the first direct proof of gradient bounds that doesn't appeal to C1 alpha estimate whatsoever at any stage as a quantitative estimate. So we do not use this anyway. So we do the first direct proof that doesn't appeal to C1 alpha estimate. So this is a technical novelty, an inside technical novelty, which is worth reporting because at least in the whole literature I know, and I don't know, of course, the whole literature, but I can say that after many years, I know quite a lot of the literature. And this has never been done. So the proof is a long tour de force that exploits essentially every bit of known regularity and builds on it with new ideas. So we use nonlinear potentials and non-uniformly elliptic and nonlinear potential theoretical methods. We relax estimate at the fractional level. So we have a local problem, but we treat it as it was non-local. So we use a fractional variation of the classical Bernstein method to get a priori estimates. We use a fractional variation of Moses iteration, where the gain is not geometric, but linear. And then we use a potential theoretic and fractional version of the Giorgi type iteration. Essentially, we have non-differentiable coefficients. We have Hilder coefficients. So we differentiate the equation in a fractional way, and we do everything at a fractional level. So let's see. So we first get this fractional version of Moses iteration that appears in a certain sense in also other papers in the literature, but not in this way, because it's not done to get higher integrability, but to get some higher differentiability. So we get a direct proof of L infinity via a fractional and nonlinear potential version of this the Giorgi's iteration. And in particular, we use, in order to get the first step, we use certain weaker form of non-uniform ellipticity, that's a degenerate version of uniform ellipticity and monotonicity that appear to be useful in stochastic homogenization, random conductance, random structures, and so forth. In fact, immediately after our paper, our technique was reemployed in a paper by Lucas Koch and Matthias Schaffner on stochastic homogenization. Because in homogenization is typical that when you go to homogenized operator, you lose certain ellipticity properties when you go to the limit. You retain some weaker notion, but you lose strong uniform ellipticity properties. Okay, in order to describe this fractional variation, let me go to the classical Bernstein method to prove, how do you prove, let's say, for the fast proof of the fact that the solution to the P Laplacian operator are bounded. So what you can prove, what you can argue in the following sense. This is very formal, so this has to be made precise via approximation and so forth. But let's imagine that everything can be done. Everything can be justified, in fact. Okay, so in the classical Bernstein method, you start from a nonlinear equation, you differentiate the equation, and then you use the differentiated equation to show that a certain power of the gradient is a subsolution of a linear uniformly elliptic equation. Being a subsolution to a uniformly elliptic equation means that you are bounded from above. But since you are positive, then a bound from above is a bound everywhere. And this is essentially the method that Uelzer and Uhlenbeck used to bound the solution of the P Laplacian. If you look inside, it's something like this. Okay. Now, if you go to the proof, how do you prove that solutions to linear elliptic equations are, in fact, subsolutions are bounded from above? Well, you do the classical, for instance, the George's technique. That is, you use a Cacciopoli typing equality of this type on level sets, where this is the positive part of V minus K. K is the level, and this is the truncation of the function. So this is the classical de Giorgi's iteration, which is based on this Cacciopoli inequality, where you control a higher order term, like the gradient, with the solution itself. So it's very often called a reverse Poincaré inequality. Poincaré means that you control the function with the gradient, so a more regular object with a highly regular object. Here you do the opposite. Okay, in this setting, this is impossible because you cannot differentiate the equation because the coefficients are either continuous. So you cannot develop the equation. You cannot develop under the sign of divergence. So what we do a fractional differentiation, and we prove a fractional intrinsic version of the Bernstein technique. So we prove that a certain function which has this growth, V, satisfies this renormalized fractional Cacciopoli inequality. So in the previous Cacciopoli inequality, you have a gradient. Here you do not have a gradient. You have a fractional Gallardo semi-norm, which is some sort of fractional gradient. On the right-hand side, you do not have only V. You have V, but a function that depends on the L infinity norm of V. And the L infinity norm of V is the L infinity norm of the gradient. And then you have the terms accounting for the presence of coefficients, because this is without coefficients. Now you have coefficients, so you have additional terms. Now, why? So the difference between this and the previous one is in three parts. You replace a full gradient by a fractional gradient. You replace a right-hand side depending on V with something which makes a renormalization. And then you have something arising from coefficients. And this takes into account the regularity of coefficients. This power of the radius takes into account the regularity of coefficients. That is linked to Hilbert continuity of coefficients. So why we make this normalization? We would like to prove that V, that is the U, is bounded, and then we have an inequality that involves a bound on the L infinity, because we want to have a rigid homogeneous inequality with respect to V. So this is formally homogeneous with respect to the iteration norm. So let me go to the next slides. So this is the classical Cacciopoli inequality, let's say for the P Laplacian operator, where V is du to the P. If we apply our estimate to the P Laplacian operator, we obtain a similar estimate, but we are replacing the gradient with a fractional gradient. So both of them are uniformly elliptic estimates. And observe that they are both homogeneous with respect to V, because this is a square and this is a square. If we go to the new Cacciopoli fractional inequality, this is formally homogeneous with respect to V, and all the non-homogeneity has been renormalized together with these coefficients. And on top of that, there's the effects of coefficients. Iterating this can be done. Iterating this can also be done. Iterating this is much more difficult. But you can hope to iterate because this is homogeneous. So in a certain sense, this renormalization brings this inequality back to the uniformly elliptic regime. Okay, so in a sense, we are delocalizing the problem. And we are reading Hilbert continuous coefficients as a sort of fractional differentiability. Now, since you start from a local equation, having a fractional inequality is not easy. You have to delocalize, and to do this, we use some sort of nonlinear atomic decomposition that takes some ideas of atomic decomposition on Bezoff functions, but directly applied at the PDE level. So in a certain sense, we use a delicate, some sort of Bezoff dyadic decomposition that usually come from little Paley decompositions where atoms are not general bump functions like harmonic functions, but are themselves solutions to suitably localized nonlinear equations. Because if you use typically classical dyadic decompositions, they work in the linear case. So we want something in between that fits the nonlinear thing. So we modify this dyadic decomposition, taking as atoms solutions to nonlinear equations. So they fit better in nonlinear equations. And this is essentially what I was saying by words. So we have to find some sort of dyadic decomposition using nonlinear atoms that fitting the nonlinear scale. So we are micro-localizing the analysis of these degenerate equations. Also, this type of Bezoff decompositions were in fact introduced in previous work in calculus operations with Christensen and applied to this in this setting to derive fractional estimates and the Georgi fractional iterations in the papers you have seen in the previous talk. This was done many years ago. Particularly was done before this wave of fractional regularity started with Caffarelli. In fact, also Caffarelli makes use of similar fractional inequalities, but these Cacciopoli inequalities later used by Caffarelli and others are much easier to get because you just have to test the equations because they start from non-local equations and then they get non-local inequalities. We start from local equations and then we have to get non-local inequalities, which is a different story. After that, we arrive at similar fractional Cacciopoli estimates, but these were done many years independently before BIT in this business paper and so forth. Okay, how do we do this? We go into this dyadic decomposition. So we take these difference quotients and we have estimates in Minkowski spaces. So we relax the fractional spaces to Bezoff spaces where the second index is plus infinity. These are so-called Minkowski spaces. And this is done at the level of Bernstein method. So we take V, which is due to the P, we take the truncation, and we show that this satisfies a Cacciopoli inequality. So everything is involved at this stage. So we take a certain rate of H, which in the little Paley frequency way of thinking means that you're taking an annuli which is very far, So if H is small enough, this means that you're looking at a very far annuli in the frequency space. And then we take a lattice decomposition, whose size is like H. And on each one of these cubes, you solve a frozen equation. You take the solution of this frozen equation as an atom, and then you attempt to a decomposition of U as a sum of these bump functions plus coefficients. Why they do behave as atoms? Because atoms, they have these properties. All the derivatives can be bounded by the radii. This holds for any type of derivative. We do not need any type of derivative. We just need one derivative. And this is true for solutions because this is the classical Cacciopoli type inequality for the differentiated equation. So this is very technical, so I don't pretend that you're following things at this stage. I do it for completeness just to give some, let's say, to give some hints. But I mean, if you feel confused at this stage, it doesn't depend on you. It depends, first of all, on the fact that this is very technical and probably on me that I'm not explaining this well enough, but it's a technical stuff, believe me. And the proof of the previous theorem takes more than 70 pages, so it's not a trivial proof. Anyway, after we get this Cacciopoli inequality, we are back in the game of this classical de Giorgi's iteration, because then we can apply fractional Sobolev embedding theorem and getting this reverse Hilder inequality on level sets with remainder. So you see, If the blue and red parts are not there, this is the classical reversal of the inequality on level sets. But there are two additional host guests here, which is not very welcome. The one coming from coefficients, and especially the one coming from the non-uniform ellipticity. So in some sense, this function h is equal to 1 in the uniformly elliptic regime. And when there are no coefficients, this term disappears. So you have a purely classical reversal of the inequality. Otherwise, you have these two guests. Okay, the idea is that we iterate this using this as a constant. But the advantage of this inequality is that if you are just iterating this object, this is homogeneous and can be iterated because this piece is homogeneous as this one. You see, 2 chi, 1 over 2 chi, 2, 1 over 2, and chi is larger than 1, and it depends on fractional Sobolev theorem. Okay, now there's a magic fact happening, which is a hidden fact known to experts. In the Georges, Moses, any proof, if you look at C alpha estimates, C0 alpha estimates, constants depends exponentially on the ratio of the eigenvalues. If you look at C alpha estimates, but if you look at L infinity estimates, this dependence is still polynomial. And we use this very hidden fact, which is never noticed. In fact, we now introduce these nonlinear potentials. This is having Mazia-Wolf potentials. And these are general form of potentials. In fact, it reduces to, for certain suitable choices of sigma and theta, they reduce to Riesz potentials and to Wolf potentials. Otherwise, it's a different potentials of the type used by having a Mazia. It is what it is. Okay, then we prove the following hidden fact that incorporates the information I gave you before on the polynomial dependence on the ratio of the eigenvalues in a nonlinear potential theoretic way. So, and this is an abstract fact. Assume that you have a function v satisfying this reversal of the inequality with remainder for every scale. Then you can prove a pointwise bound on v with a polynomial control on the constant. You see, you can iterate going to an integral norm to a pointwise norm as far as chi is larger than 1. And in fact, when chi goes to 1, this goes to plus infinity. And this is hidden in the work of Kilpelangen and Mali. Okay, there is some information about that, but if you this explicit version is non-trivial and it can be found in this paper by Cristiana De Filippis and myself. Then take a reference ball and apply this to V, which is the gradient, and you will get this inequality. You see, you want to get a bound on L infinity, but L infinity is still on the right-hand side. So your only hope is that these powers are less than 1. And you see here is the L infinity norm of the gradient. So you opt for two things, that under the choice of the bound PQ and alpha, this is less than 1 and this is finite. And the magic fact is that after all these pages of computations, then exactly the sharp bound under which you hope to get regularity in an optimal way, because it's given by the counterexample, allows you to both the things. The potential is bounded, and this exponent is less than 1. Once you do this, you can iterate You can use Young's inequality. And after this, you can use a standard iteration lemma to reabsorb this and to get the L infinity bound. Once you get the L infinity bound, you are in a sense back to the uniformly elliptic regime, and you can adapt these methods, the more classical perturbation methods. But up to here, you got an L infinity bounds, and you never used C1 alpha estimates. You just a direct proof. Okay, this is everything I had to say, and I would like to stop here for the two talks.
Thank you. Any questions? Well, let's thank the speaker again. Thank you very much again.
I see Juan Manfredi, my friend, who is saluting. I mean, one of the founders of the theory. I mean, if you want to know more about all these details of C1 alpha and blah, blah, there is his thesis or there is him himself there. And okay. Bye-bye. Thanks a lot. Ciao, ciao.